Okay, so thank you in first place. Thank you very much for the organizers for the opportunity to share my work. I'm going to talk about implementation of a Maxwell demon using electronic circuits and discuss the macroscopic limit of this device. So first I would like to mention very briefly, because I assume that the audience is familiar with the idea of a Maxwell demon. So a Maxwell demon is a being or a device that is able to perform measurements and feedback control on a given system. And in this way, even if the system initially is in thermal equilibrium, by this process of measurement and feedback control, the demon can develop gradients of pressure or temperature, for example, in this initially equilibrated system. And in this way, it can extract work out of it. So this, as you know, this was a central thought experiment to establish the relationship between information theory and thermodynamics. And since 2007, there has been a lot of experimental implementations of this idea. The first one working with macromolecules, and then going into electronic circuits, colloidal particles, and so on. But something that all these implementations share in common is that they all work in microscopic regimes. And by that I mean that they involve single molecules, single atoms, single electrons, or single photons. And this is very natural. This is in line with the initial notion, the original notion of a Maxwell demon, that was believed to only be able to violate or to produce an apparent violation of the second law in the case in which it had sufficiently fine control and perception of individual molecules. And so basically what we want to explore in this work is what happens if we scale up a Maxwell demon. So if we make the demon more bigger, if we make it bigger, so it has a more coarse control on for example, on this door, or it has less resolution to observe the state of single molecules, what happens? How is the performance of the demon affected by that? So in another way, what we can ask is, if a Maxwell demon can only be microscopic, at which scale does it stop working? And if that can be prevented in some way, if we can in some way prevent a demon from stopping working, as we make it more macroscopic. So we will explore these questions in an electronic model. And to explain that model, I first need to explain what is the Siemens inverter. Massimiliano already mentioned something in the previous talk, in the first talk this session. So a Siemens inverter is this circuit I am showing here, which involves two transistors of different kinds. The transistor up here, do you see my pointer?
Yes.
Okay.
Yes.
This transistor here is a PMOS transistor. The one below is an NMOS transistor. The one on top becomes less conductive as the input voltage is positive, and the one below becomes more conductive as the input voltage is positive, and the reverse happens for negative input voltages. So the transfer curve of this Siemens inverter, so the curve giving us the output in terms of the input, looks like this, because when the input voltage is positive, this transistor is less activated than this one, so the output voltage will equilibrate to the voltage V2 here. And when the input voltage is negative, this transistor is more activating than this one, so the output voltage will equilibrate with this reservoir at voltage V1 here. Okay? So, so this is a typical transfer curve for a Siemens inverter, and something that I will introduce now because it will be important later is that very close to the center of this curve, the Siemens inverter works as a linear amplifier, as a linear negative amplifier with some amplification factor alpha. So, to explain the idea, to construct a Maxwell demon out of this inverter, I will first consider the equilibrium case. So an inverter, a Siemens inverter, is powered by some voltage bias, some voltage difference between terminals B1 and B2, which will produce a current going from the highest voltage B1 to the lowest voltage B2, which is this current IS here. So let's consider first the equilibrium case in which B1 and B2 are 0. Okay, so in that case, we know that the system will attain an equilibrium state, and so the probability distribution for the different states that the system can have that are different voltages for the output, that distribution will be given by the Gibbs distribution, so it will be e to the minus the energy of each state, and the energy of each state is given by this. It's just a quadratic in the potential. So the distribution will be a Gaussian distribution and discrete Gaussian distribution. And if we observe, if at any given point we observe a negative fluctuation, a negative value of the voltage, we will consider the following feedback protocol, in which, given this value, this measurement of the output of inverter, we will feedback on its input with a minus some amplification factor alpha prime, which is different from the one I introduced before, times the voltage that I observed. In that case, if I do that, then I will have a negative output, and at the same time I will have a positive input. So I can consider that the upper transistor will be shut off, and that momentaneous negative voltage will be compensated by charge flowing from the lower reservoir into the conductor here. So I will generate an upper, an upgoing current. Okay. If instead I observe a positive fluctuation, then the same feedback protocol makes the input negative while the output is positive. So that momentarily excess of charge in this conductor will be more probably dissipated through the upper transistor into this reservoir. Okay, so in this way I can, by this measurement and feedback control, I can create, even if the system is at equilibrium, it is not biased by any voltage difference, I can generate a current in the direction I want. And this effect also survives even if I apply a small downward potential difference. Okay, and in that case I will be rectifying currents. So so far I have explained only the feedback protocol that might be implemented by some daemon or agent, and what I will consider now is the construction of an autonomous daemon, and for that I need to provide an explicit model for this agent. And one can very quickly realize that basically what we need is a negative amplifier, and that can be implemented by a second Siemens inverter, which is powered by some voltage difference between terminals B3 and B4. Okay, so in this case, so now from now on, I will consider this full circuit formed by two inverters, and in this case we have a bipartite system. And there will be two currents, two electric currents that will be established at the steady state, one flowing through the system, through the first inverter, and one flowing through the daemon, which is the second inverter. So I can define partial entropy production rates at the steady state that will be just given by, for example, for the system, it is just the current through the system times the voltage difference across the system. The same for the daemon. And of course, the total entropy production, which is the sum of those two contributions at the steady state, must be positive. So whenever the daemon actually manages to make the current through the system to go in the upward direction, then in that case, the entropy production on the system side will be negative. So we can define the thermodynamic efficiency of the daemon in this way, whenever the current through the system is negative. And okay, so to continue, I will discuss how one can model this circuit at the deterministic level. So one can very easily write down the equations of motion for the two dynamical variables of this circuit, which are the output voltages at each inverter, so the voltage B and the voltage B in, which is the input for the first inverter, but the output of the second. And so one can very easily write the dynamical equations based on the currents of the electric currents through each transistor that we know, because we know the IV curve characterization of each transistor. And one can very quickly see that in the deterministic treatment, the output voltage B is always between B1 and B2, and the output voltage B in is always between voltages B3 and B4, and that implies that both currents are always positive. So no rectification is possible at the deterministic level. The deterministic dynamics does not allow rectification of the current through the system for any parameter. And also something that will be important later is that this set of deterministic equations displays a B-stability whenever the product of the amplification factors of the system and the daemon is larger than 1. This alpha square quantity that I define here is larger than 1. This system will become B-stable. We'll have two fixed points at the deterministic level. So how is the modeling of this device at the stochastic level? Well, for this, basically what one can consider is that conduction through each transistor is a stochastic process in which shunts can shunt from one terminal to the other in one direction or in the reverse direction. And so each transistor is associated with two shunt rates that depend on the value of voltages at its terminals. And using the IV curve characterization of each device supplemented by the local detail balance conditions, one can map any given circuit into a Markov shunt process in a thermodynamically consistent way, as explained in this article. So by doing that, we obtain a master equation like this one for the evolution of the probability distribution over the possible circuit states that are given by this vector with the two voltages. And here we have the shunt vectors telling me how the voltages change in each transition. And here this voltage BE is the elementary voltage by which each voltage can change during a shunt, okay? Which is just the electron, the charge of the electron, the positive charge of the electron over C, where C is a value of capacitance that characterizes the device and that will become important later. So given the master equation, we can, with different methods, compute the steady state. For example, here I show three different steady states for the monostable phase, for the critical point in which we enter into the B-stable phase, and for the B-stable phase itself. And for any set of parameters, we can compute the steady state in this way. And we can, given the steady state, we can compute, for example, the average currents. For example, in this plot here, I show the average current as a function of the voltage bias through the system and the voltage bias through the daemon. And we see that if the voltage bias through the daemon is sufficiently high, then I can make this current, the current through the system, to be negative. In that sense, I am making the current through the system go against the voltage bias that is applied to the system, which is the first inverter. So rectification of power at the system side, and so the entropy production at the system side is negative. So I have a working Maxwell demon made out of Siemens technology. So what I would like to discuss now is what happens to this demon in the macroscopic limit. So the macroscopic limit here involves, which is basically the one Massimiliano talked about in the first talk, is related to actually increasing the size of the transistors involved in the circuit. So I won't go into the details, but each transistor that is drawn here in the circuit diagram has a structure like this one with two different length scales that are relevant, which is the length of the conduction channel and the width of the conduction channel. And we can consider a particular scaling strategy, which is keep L fixed conduction channel. And under that scaling, what we can see is that the typical capacitance that I introduced before increases with the scale. So the elementary voltage, which is the change in voltage in each shunt, decreases with the scale. And also the average currents for fixed voltages increase, because what happens when I increase the width of the conduction channel is that the Poisson rates associated to each transistor also increase linearly with omega. So we can consider the inverse, if we want C, or equivalently the inverse of the elementary voltage as our scale parameter. And it can be seen that under these conditions, the probability distribution satisfies a large deviation principle in terms of this scale parameter omega. This is better explained in these two articles. We will work from now on in that limit. So if we take the master equation and we just introduce these ansatz, we see that we obtain a dynamical equation for this rate function f, okay, which is minus the log of the probability distribution over the scale parameter. So instead of working with the probability distribution, we can work with this rate function f, and this rate function f evolves in this way that Massimiliano also discussed. So the minimum of this function follows the deterministic dynamics. If we do a quadratic expansion of this rate function around the minimum, we obtain a Gaussian approximation. And we can use this Gaussian approximation to compute averages of different observables to first non-trivial order in the scale parameter. And by doing that, we can obtain an analytical expression for the current through the system that has this. But if we take the approximation, we expand it to first non-trivial order in the bias applied to the system, delta Vs, then we obtain this simple expression. So now I will discuss, based on that analytical result, what is the scaling behavior of this device. How the behavior, how the performance of the daemon changes as we change the size of the system. So the first thing we can see is that the current through the system can only be negative if the scale is below a maximum scale, okay, which is just the amplification factor of the daemon over the voltage bias applied to the system. Okay, so if I want to make the device work at larger scales, I need to put here at the daemon side an amplifier which is more powerful. Okay, that has a larger amplification factor alpha D. Equivalently, I can consider that for the current through the system to be negative, I need to have a minimum powering voltage applied to the daemon, delta Vd, which is given by this expression that, as we see, increases logarithmically in the size, in the scale parameter omega. Okay? And so it is tempting to say that by just increasing logarithmically the powering of the daemon, we can make the daemon work at any scale, but that is actually not correct, because what happens here is that if I increase the powering voltage of the demon only with all the other parameters fixed, I enter very quickly into the bistable phase, and this expression for the current is only valid for the monostable phase. So but anyway, this argument can be corrected. So if we consider that the parameter alpha squared that tells me whether I am in the monostable phase or in the bistable phase is fixed, I can fix this parameter and consider this particular scaling in which I very slowly reduce the bias applied to the system according to the scale, and I even more slowly increase the bias applied to the demon according to the scales, also in a logarithmic way. And in this way, with this particular scaling of the powering voltages in terms of the physical scale of the device, we can see that the power rectified at the system size becomes constant, becomes independent of the scale, and the entropy dissipated at the demon side in scales like this quantity, okay, which can be written as log of omega over omega squared. And this scaling is verified by Gillespie simulations of the device, not only in the monostable phase, but also at the critical point and at the bistable phase. All phases seem to have the same scaling, even if we derive the scaling also only for the monostable phase. So the conclusions are that for fixed powering, the demon stops working above a maximum scale. But if the powering is scaled appropriately, the demon continues to work, but with a decrease in efficiency. Okay. So there is a very obvious question that is the following. I mean, is this optimal? Is this scaling that we have obtained for the decrease in efficiency as a function of the scale optimal one, or it is possible to do better than this? This is an open question for us, and it relates basically to the general question of what are the thermodynamic limits of amplification. In this particular implementation of a demon, we used the amplifier we had at hand, which was just another Siemens inverter, but it is not clear for me, at least, if there is no another possible electronic implementation of an amplifier which is more efficient, more thermodynamically efficient than a Siemens inverter. So to close, to finish, I would like to mention that this is not the first proposal for a macroscopic Maxwell demon. After finishing this work, we learned from discussions with Parrondo that he had already thought about this, and there is a nice article by him. But the mechanism that he found to imagine a Maxwell demon, a macroscopic Maxwell demon, was completely different. In this case, he uses the symmetry breaking in a second order phase transition to transfer information from the microscale to the macro scale. In our case, we do that in an active way. And another difference between our proposal and his is that our proposal is an autonomous Maxwell demon, and that in his proposal he needs to have an externalization running cycles on the system, and the work extraction per cycle is limited by KT log 2, which is it is due to the fact that he extracts only one bit of information about the microscopic state of the system in each cycle. And from a more general viewpoint, we think that our work is interesting because it shows that the link between the microscopic limit and the fact that fluctuations can usually be neglected in the microscopic limit, and thus the dynamics of the system becomes deterministic. This link can actually be broken if the power, can be broken out of equilibrium if the thermodynamic resources are scaled appropriately with the size of the system. So basically, the take-home message is the fluctuations can survive the macroscopic limit in non-equilibrium settings. So with that, I finish.